Good morning, ladies and gentlemen. May I have your attention, please? Thanks. Let's go ahead and begin our discussion. So we've got a big day today. We're going to go ahead and investigate the relationship between continuity and differentiability of a function. We're also going to practice a little bit more with our indeterminate forms to make sure we're comfortable when and how to apply L'Hopital's rule or in an indeterminate form when we're evaluating limits. So let's go ahead and get started. Firstly, we always want to begin with direct substitution to see what we're working with. As x goes to 0, I know that tangent goes to 0, minus 0, all over 0. By golly, I generate an indeterminate form. However, is it an indeterminate form that authorizes the use of L'Hopital's rule? Brendan?
Yes.
Yes. So if I have an indeterminate quotient, 0 over 0, or plus or minus infinity over 3, then I'm authorized to use L'Hopital's rule, which is applied by doing what? So how do you apply L'Hopital's rule? Courtney?
You take the derivative of the top and the derivative of the bottom separately.
Absolutely. So we're not doing the quotient rule as the main place where students can make mistakes. We're taking the derivative of the top, we're taking the derivative of the bottom separately, and then we're trying again. So let's go ahead and do that. I know that tangent differentiates to secant squared of x minus x differentiates to 1 all over 3x squared. Let's try again. As x goes to 0, secant 1 over cosine is 1 over 1 is 1, minus 1 is 0, and then 0 on the bottom. So it looks to me like we got another indeterminate quotient. So we can go ahead and apply L'Hopital's rule again. Now we're going to have to go ahead and use our derivative rules, right? And our derivative chain rule here. This is overall a power function. So when I differentiate secant squared of x, I'm thinking secant of x quantity squared. So here we go. The derivative of power is exponent times the base raised to 1 less, so that would be the first, then times the derivative of the base. I need the derivative of secant x, which spits out another, right? Secant x tangent x. Oh, goodness gracious. But we can see the parts here. So there's exponent times the base raised to 1 less times the derivative of the base. Minus the derivative of 1, a constant of 0, all over 6x. All right, we're close now. So here we go. One more time. As x goes to 0, secant is 1 over cosine of 0 is 1. That's 1. So 2 times 1 is still 2. Then we get times the tangent, and that sine over cosine, that is 0. So I get 0 for the top. Over 6 times 0 is 0. Oh my goodness gracious. 1, 2, 3. So one more time. We've got L'Hopital's rule. The limit as x goes to 0. What rule are we going to use here? Oh my goodness gracious. So it looks to me like multiple functions of x occurring, right? Connected by multiplication. I'm going to have to use what rule? Riley? The product rule. Do you want to clean this up a little bit? I think I'm going to join the secant x times secant x. Can I make that as my one function, secant squared of x, and then I'll make tangent of x as my second function? Similarly, I'm going to go ahead and rewrite this once. So I don't mess up, I'm going to reduce the 2 over the 6. I'm going to write secant squared x as my first function plainly, so it's easy to see when I apply the product rule. I'm going to write the denominator then as 3x. And now it's easier to see. We're going to do the product rule. Everybody ready? Awesome. Let's do it. So here we go. The derivative of secant squared x is 2 secant squared x tangent x times the second function plus the first function times the derivative of the second function. Tangent x differentiates to secant squared x all over the derivative of 3 times, hey, I don't know what that top evaluates to, but by golly, I know we're done with L'Hopital's rule because I've generated a constant on the bottom. That's not going to fill any either of my indeterminate quotients, 0, 0, or infinity. I know I'm at the end of the road one way or another. This is the ugliest secant I've ever seen in my life. It's marginally better. Let's see if I can avoid a rewrite here. We already know that as x goes to 0, secant goes to 1. So this is 2 times 1 times 0 is 0, 0, plus. This is going to be 1 times 1 is 1 over 3 is 1/3. I'm getting 1/3. Is that indeterminate? No. Finally, we reached the end of the road, and I'm going to put equals 1/3. Raise your hand if you had 1/3. Anybody else have 1/3? Awesome! My goodness gracious, but I certainly want to verify graphically and numerically. So I'm going to go ahead and go into my original, and I want to just do a quick check. Can I write a check? Yo. Okay, so I want to see what happens to, oh, I better check for advanced algebra. We're in radian, good. We're going to go ahead and check and see what happens with tangent of x. Oh boy. Close input. Minus x, close numerator, all over x cubed. I'm thinking the math 3 shortcuts, but like the bomb. And I want to see what happens when x goes to 0. So I'm going to, can I zoom to enter? Oh. One of those heartbeat monitors, looks like. Old school. And I'm going to zoom to enter. Okay, so here we go. As x goes to 0, what's happening to my function? Jump. So as I trace 0, enter, it's not producing a y value. How come? The expression is clearly undefined at x equals 0 because it generates a 0 in the denominator fraction, and yet it looks like, gosh, we're really close to 0.3335. Other side, 0.3335. So our numerical with numbers and our graphical with the picture seems to verify what we found exactly algebraically. So that's pretty sweet. And deserves a screenshot. Yeah, that's pretty neat. Awesome. What questions do you have about our triple decker? Is it fun doing what we thought 3 times? Calc BC math sort of way to start your morning. All right. Let's go ahead and show you your indeterminate forms then. What are indeterminate quotients, Grace?
0, 0, and infinity or infinity.
Awesome, thank you. What are our indeterminate product? Marissa?
0 times infinity.
Yeah, I said product earlier. We were just worried about one product. That's 0 times infinity plus or minus, or infinity times 0, either order, because it's a product difference. What's our indeterminate difference, Vivian? Infinity minus infinity. Awesome. And we've got several indeterminate powers. So what's one of them? Sophia? Infinity to the 0, right? This infinite, right? Infinity to the 0. If we multiply infinity by itself, it's trying to get to infinity. If we raise something to the 0 power, it's trying to get to 1. We've got a battle going on, right? And so who's going to win? We don't know. What's another indeterminate power? Tyler?
0 to the infinity.
0
to the 0.
To the 0. Excellent. So 0 multiplied by itself is trying to go to 0. Raised to the 0 power is trying to go to 1. Who wins? Well, we've got a tug of war. We don't know. And last indeterminate form, right? What's our final indeterminate form? Kobe?
1 to the infinity.
1 to the infinity. Here, right, we're thinking if we multiply 1 by itself an infinite number of times, the result is 1. What's indeterminate? We'll recall that this quantity in the base is approaching 1. If we're to the left of 1, like 0.9, when we multiply repeatedly, it's shrinking towards 0 overall. If we are slightly greater than 1, right, then it's ballooning towards infinity when we multiply by itself repeatedly. And that's why 1 to the infinity is indeterminate. Awesome. Questions about your indeterminate forms? Which of these authorize these to L'Hopital's? Danny?
Quotients.
Yeah, only the top quotients. That's old news. And review from A, B, and C. You guys are doing that great. Okay, let's go ahead and pause the recording and take care of our OTL number 6, please. Okay, ladies and gentlemen, so we've got our super link reminder on top, and I want you to think back to, right? Think back to our rip-roaring rendition of Sesame Street. One of these things is not like the others, okay? Now, if it helps, I could hum, right? But I know that by playing that, you guys already have it in your head. And so, what is going on here? Well, I want you to focus in on these closed circles, okay? For each of these x equals c values, call them x equals -4, x equals -2, and x equals 1. I want to go ahead and fill out our grid with your partner. Is f of x defined? Question 1. Does the limit of f of x as x approaches c exist for each of those c values? And is f of x continuous at x equals c? Go ahead and do that with your partner now, and then share your findings. Make sure that your grid agrees, because then I'm going to have you share with the whole class. So once again, go ahead and answer those questions and complete your grid. Be ready to share your findings with the whole class.
That's supposed to be one.
Martin?
What's the last
Grid.
one?
Or the grid.
That's why.
Right here?
One on the bottom.
Yeah, I copied and paste. I did.
Yes.
1.
Yeah.
Thank you. Yes, it's supposed to be. Everybody, please make that change. Thank you, Kobe. Good catch.
Last one was 6.
Yep.
Okay, let's go ahead and see. Is f of x defined at c equals -4? Riley?
Yes.
Yes. You want to just keep going with Y's and N's all the way across? Do you check with Vivian?
Yeah,
Okay, go ahead. Yes? Yes? Yes. Okay, at x equals -2. Emily and Tyler?
Yes. Yes. No.
Okay, everybody take a look at line 2. We've got our first N for no. Raise your hand if you have the same entry with your... Yes? Okay. X equals 1. At x equals 1, is that defined? Does the limit exist? Overall, and is that continuous? At x equals 1. Last line, Sophia and Grace.
Yes, no, no.
Yes, no, no. Okay, so now what I want to do is I want to focus in on our no's for continuity. So what's going on with our no's for the continuity, right, question here that will help us get our definition? Well, I think, right, in each case that we've got, do we get yes, yes, yes? Oh, so our function's defined, and yet it's not always continuous. Sometimes when our limit exists, it's still not continuous. And if the limit doesn't exist, then it's not continuous either. Okay, so let's go ahead and do one more thing.
Bless
Cue the video, bless you. I mean, cue the video recall. Scan. And the other one I did, it had balloons. So these aren't the same video. One has balloons. I'll show it to you next time. So here we go. One more chart with your partner. Be ready to share. Focusing on the closed circles, please. Is f defined? Does the overall limit exist? And is f continuous? Looks like I didn't get 10 in there. Okay, ladies and gentlemen, let's go ahead and share our findings for our second chart. And starting at x equals -8 from left to right. Courtney and Danny.
Yes, yes, no.
Quick survey of the class. Raise your hand if you yes, yes, no, in order. Hey, that's great news. At x equals -2. Is f defined? Does the overall limit exist? Is f of x continuous? Here we go. Sydney and Kobe.
Yes, no, no.
Raise your hand if you had yes, no, no. Oh, and when to go at x equals 6. What was going on at x equals 6? Grace and Sophia.
Yes,
Yes, no, no. All right, time to look at our trends. So as we see in our chart, when our function was not continuous, right, when our function was not continuous, we had either issues with the overall limit, right, with the overall limit, or, again, overall limit. What is it that made it continuous? Well, my chart just wasn't quite long enough. But at x equals 10 here, we've got continuous. And so what has to be true in order for our function? Right? What has to be true in order for our function to be continuous? And can we write that in an equation? And so what must be true for a function f of x to be continuous at x equals c? And I'm going ahead and set a template here. Oh! I want you to use an equation. Okay, so let's go ahead and with your partner now write an equation. You need but just like all right, moment of truth. Dun 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 dun. Riley.
C is the equal limit as x approaches C.
perfect notation, perfect letters, raise your hand if you had that. So the limit of f of x approaches c has to equal the value of the function at x equals c, and that takes care of at x equals 10. Here we have a continuous function. The overall limit exists because the left-hand limit matches the right-hand limit. It equals the value of the function, right? The function is defined there, and so we're good to go. Nice job. So what are we going to do? Well, we're going to go ahead and determine continuity algebraically, right? Verify graphically and numerically. Then we're going to switch gears and with a rip-roaring story that I'm going to share with you. We'll develop our requirements for differentiability as well. Okay, so and now, the moment some of you have been waiting for. No, it's not the bell. Mr. Fritz's story of differentiability in words and pictures. Hang on, I have to get in character. So, as we embark on this journey through AP Calculus BC together, there's going to be some bumps in the road. And yet, so long as our functions are smooth and well-behaved, right, we stay within our realm of differentiability. That is, if we were to zoom in at any one x equals c value here, further and further, our train tracks would resemble more and more of a line, and that's what we call locally linear, or local linearity back from AB. So smooth, well-behaved, locally linear, that is differentiable. And yet, sometimes life throws us some kinks in the road, so to speak. And while we might still be continuous, that is, we could trace along the train tracks with our pen and pencil without having to lift it up, or the limit of my function as x approaches c is equal to the value of the function at x equals c, and yet we're not differentiable because the left-hand slope does not match the right-hand slope. So this is not differentiable. If the limit of the slopes approaches positive infinity on one side and negative infinity on the other side, it's our BC definition of a cusp. That is, where one side the slopes are approaching positive infinity, and from the other side the slopes are approaching negative infinity. We're dealing with a cusp versus an abrupt change in direction where the slopes are defined, right? The slopes are defined here. That is a numerical value, and yet they're different. So the overall limit of the slopes do not exist. Therefore, it's not differentiable. This is what we call a corner. In either case, the function is not defined. Oh, that's the second time this week. And finally, back to our BC train. If we've got a discontinuity, then we wreck it for differentiability because there's no place to hang a tangent line, right? If we were to zoom in here, we wouldn't be locally linear because we've got a gap, we've got a skip, we've got our function is not defined here. And so automatically, if a function is discontinuous, I'll say if discontinuous, then automatically not differentiable. How do we do with our story in pictures and words? Okay, great. So then, which of these are differentiable for all x? Scan. Which of these are differentiable for all x? And we've got options 1, 2, 3, 4, 5. And you're all combinations. I hope you're taking this opportunity to quietly check with your partner so that you don't think I'm picking on you. I'm picking on you and your partner when I'm calling you. Don't need to be singled out. Which of these are differentiable for all x? Brendan and Marissa? 1. 1, is that it? Raise your hand if you had only 1. Only 1? Oh. Gosh. Ain't no hell for a stepper. Which are differentiable for all x? Round two. Grace and Sophia?
The first one?
First one? I don't know, what is it? That's it? Raise your hand, your first one only again? Oh, gosh. Well, so differentiability, right? Differentiability implies continuity. So if we're differentiable for all x, then automatically we must be continuous. What happened, right, when we weren't differentiable? Well, if we weren't differentiable, we could have a corner, we could have a cusp, right? We could have a discontinuity. And so I want to go ahead and, because you didn't get the story picks, right? So then make sure that you have cusp for when you have an infinite tangent, right? Positive on one side and negative on the other. We got to label that a cusp versus a corner. I knew we'd get it in these picks. What was the problem here? Discontinuity. Overall limit existed, but there's a discontinuity. And for both of those, discontinuity. And that's what made it not differentiable, right? For all x. Problems here, corner, discontinuity, right? An infinite discontinuity in this case, and discontinuity, a step discontinuity in that case. Great. All right. So if f is differentiable at x equals c, then it's automatically continuous at x equals c. Is the reverse true? That is, if a function is continuous, is it then automatically differentiable? Sophia?
No.
No, here we see example in the second pick where that's continuous but not differentiable. All right, so we've got our pieces in place. Let's go ahead and now focus our efforts on determining algebraically, right? Continuity versus differentiability. So first, let's go ahead and take a look at our pick. For what values of x is f continuous? All right, so we can use our picture in our algebraic, right, function definition in order to determine if x is continuous at x equals 0. As x approaches 0 from the left-hand side, I'm going to use a different function definition from the right-hand side. So let's go ahead and consider the overall limit as x approaches c of f of x. In this case, x is approaching 0 as my point of concern. I need the overall limit to exist to satisfy my first requirement of continuity. So I'll go ahead and consider the left-hand limit algebraically. If I didn't have the picture, as x approaches 0 from the left, I'd use which definition? Top, middle, or bottom? Tyler?
Middle.
Middle. As x approaches 0 from the left, I'm using middle, and I'm using negative x. And I'm evaluating my left-hand limit, and I'm getting
0.
Right-hand limit. If I didn't have the picture, x approaches 0 from the right-hand side, which function definition? Top, middle, or bottom? Brendan? Top. Top. I'm down as x goes to 0. X squared goes to 0. Does the overall limit exist? Yes, the left-hand limit matches the right-hand limit. This text calls them the two-sided limit. So the two-sided limits exist. I'm sorry, the two-sided limits exist and are the same. Therefore, the overall limit as x approaches 0 exists and equals 0. Next requirement, I need my function at x equals 0 to exist and be the same thing. So which definition would I use? Well, I wouldn't use the top because I'm strictly, which definition would I use now? Vivian? The bottom, and then that gives me 0. So in the simple context, we've got our picture, we've got our thing, we've got the overall limit existing, we've got the function being defined, but the most important thing is that those two are equal, so we satisfy Riley's equation. That is, the limit of f of x as x approaches c, in this case 0, equals f of c, in this case 0. That's our requirement for continuity. And all x, right, as we see with our continuous function. we needed to investigate the changing point, right, when we switch function definitions and pictures on the graph. Awesome. What's different about the second one? Well, now we're not talking continuity, we're talking differentiability. So differentiability, we need the left-hand slope to match the right-hand slope, and we need continuity. The good news is that we've already determined continuity. Continuity is a prerequisite for differentiability, as we've seen. Since we've shown that f is continuous, now we can focus on the left-hand slope. However, we still should say that. Since f is continuous, we establish that last slide. Consider two-sided slopes. What do we need? We need the left-hand slope. When I hear the word slope, I'm thinking derivative. So I need to consider the limit as x approaches 0 from the left of not f of x, but f prime of x. So as I consider the function definition, as x approaches 0 from the left, we know we're using the negative x definition, and the derivative of that is -1. So we're talking about the limit as x approaches 0 from the left of -1, which is a constant. The limit of a constant is the constant. So I get -1 for the left-hand slope. If you picture a tangent line, for x values closer and closer to x equals 0 from the left-hand side, by golly, it sure looks like the line tangent to that curve would have a slope of -1. But that's not all. We need the right-hand slope. So we're focusing now on the limit as x approaches 0 from the right-hand side of not f of x, but f prime of x. Brendan told us to use the middle function, the top function definition for that. F prime would not be x squared, it would be 2x. Is 0 in the domain of 2x my expression? Yes, so I can evaluate through direct substitution, and I get a right-hand slope of what? 0? Awesome. Does the left-hand slope exist? Yes. Does the right-hand slope exist? Yes. Is the function differentiable? No. How come? Well, the left-hand slope does not match the right-hand slope. And so, f is not differentiable at x equals 0. Since the left-hand slope does not equal the right-hand slope, the overall slope does not exist, and f is not differentiable at x equals 0. Okay, I tried to pick a very easy example, right? As we scooch in to our differentiability versus continuity relationship in algebraic calculation. So that was easy with those functions, yes? Let's go ahead and consider a different piecewise defined function. And again, we'll keep our break-even points here now. Cosine of x gives the function values if we're looking to the left or equal to 0. 2 over pi x plus 1 gives our function values if we're looking in between 0 and pi over 2. And x given by sine of x plus 2 if we're looking to the right of or equal to x equals pi over 2. All right, let's algebraically determine the values of x where f is continuous. So what do we need to check? First, I'll look at my pieces. Cosine of x, any continuity issues with the function definition itself? No. Any continuity issues with 2 over pi x plus 1? What kind of function is that? Linear, so no problem. Sine of x plus 2? No problem. So I don't need to worry about investigating for x values outside of my breakpoints. I need to check at x equals 0, and then I need to check at x equals pi over 2. So what do we need? Left-hand limit as x approaches 0. We'll use the top definition, and we're doing functions straight up. So as x approaches 0 from the left, cosine approaches 1. You guys get 1? Right-hand limit at x equals 0. So the limit is x approaches 0 from the right of, now we have to do 2 over pi x plus 1. Is 0 in the domain of my expression? Yes. So I get 2 over pi times 0 is 0 plus 1 equals 1. And f of 0, which would be top definition. So f of 0 is cosine of 0 is 1. All right. So far, what have we determined? Grace?
It's continuous at x equals 0.
Good. We've done our continuity requirement at x equals 0 because the overall limit of f of x as x approaches 0 equals f of 0, right? 1. That's great. So we're continuous here. Now what do we need? Well, we need to check here. At our break-even point, at x equals pi over 2, are we continuous? So let's go ahead and check. Right there you go. The limit is x approaches pi over 2 from the left of f is given by which definition? That's our 2 over pi x plus 1. Is that the domain of my expression? Yes. So 2 over pi times pi over 2 is 1 plus 1 is 2. You're using 2. Right-hand limit is x approaches pi over 2 from the right. I use sine of x plus 2 equals sine of pi over 2 is 1 plus 2 is 3. So without evaluating f of pi over 2, which would be the bottom definition, which would also be 3, I already know my overall limit is x approaches pi over 2 of f of x does not exist because these are not equal. So what have we learned? Discontinuous. Without looking at the picture yet, can we determine the type of discontinuity? Or what type of discontinuity would this be without looking at the picture? Riley? Step? How do you know?
Because the limit from the right-hand side and the limit from the left-hand side aren't equal, so they'd be a different y value.
Absolutely. The left-hand limit exists. The right-hand limit exists, right? They're numbers. They're specific y values, but they're different. So we can expect to see a step. Awesome. I'm going to go ahead and add that. Riley, explanation. I'm going to go ahead and add the step discontinuity, also called a jump discontinuity, depending on your text. All this is our big setup for emulator. So let's go ahead and do our new function on here. And I want to go ahead and do cosine of x. This will be great practice for our domain restriction. So how do we enter a piecewise defined function? We go ahead and divide any term by quantity, our domain restriction. So everybody, this is a great review. Let's go ahead and get our graphers. I'm going to divide by quantity. X is less than or equal to 0. Remember that was in my test menu. So second math. Everybody do it. Second math less than or equal to 6, 0. My middle function, and I'm going slow to wait, let you guys catch up. My middle function, 2 over pi x plus 1, is going to have a lot bigger. It's going to have a lot bigger domain restriction. I can't enter it 0 less than x less than pi over 2. My calculator syntax doesn't work like that. I have to enter a compound inequality with the logic and so I need x to be, I need 0 to be less than x, and I need x to be less than pi over 2. So all we're going to do, I'm going to try 0 is second, math is test, is less than, that's 5, x, and that's logic. And so I need second test, and I need logic, the and. So everybody find that? Your second math is the test menu, and I'm going to go to logic, and I'm going to select and. I need 0 to be less than x, and I need x to be less than, so back to second math, 5 pi over 2. If that's not a whopping domain restriction, I don't know what is. Last piece, sine of x plus 2 close input plus 2, divide by quantity, domain restriction. This time I want x to be greater than or equal to. Greater than or equal to would be second. Math is test. 4, pi over 2. Do you get it all? I want a window that goes from maybe negative pi to pi. So I'm going to go negative pi to pi. Oh. Maybe negative 2.5 to positive 2.5 is fine. I'll just leave it. And maybe negative 2.5 is not quite good enough because I only go to 3. So I'm going to go negative 2.5 to 5. How about for y? That's minimal changes. Let's try this. What do you guys think? If that's no good, we'll just change it. Here comes my left function. Here comes my middle function. Here comes my last function. Oh. Is Riley correct?
Yeah.
Riley is correct. We have a step discontinuity at x equals pi over 2. Are we continuous at x equals 0? Hey, it spits out the function value to the left. Just less than 1 to the right. Nothing? Oh, because I need to change functions now. Oh, just more than 1. So we're good. So we've got our left-hand limit match the right-hand limit, and we filled the circle. We plugged the hole, right? So we're good to go. That's pretty sweet. Dang, I want that picture. Why do I want that picture? Because now we can apply our continuity findings, right, for differentiability. So we're one to go. Algebraically determine the values of x for which f is differentiable, verify graphically and numerically. So as I consider my differentiability, I already know that if we're discontinuous here, our prerequisite for differentiability, right, is not met. Therefore, we're automatically not differentiable at x equals pi over 2. What do we need to check? Well, we still need to check at x equals 0, differentiable. So let's check at x equals 0. What do we need? Left-hand slope. So the limit as x approaches 0 from the left of f prime of x equals the limit as x approaches 0 from the left of function definition. 0 from the left would be cosine of x, which differentiates to opposite sine of x. Is 0 in my domain of opposite sine of x? Yes, and equals what? 0. So my left-hand slope as x approaches 0 is 0. Horizontal. Let's check the right-hand slope. So the limit as x approaches 0 from the right of f prime of x uses which definition? Uses the middle. What's the derivative of 2 over pi x plus 1? 2 over pi, that's just a constant multiplier, linear function. And the limit of a constant is the constant. What have we found? Left-hand slope does not match the right-hand slope. Therefore, f is not differentiable. Even though, right? Oh. Yeah, even though we were continuous, we're not differentiable. Well, it looks nice and smooth and well behaved, but if we were to zoom in, we can see my horizontal tangent, right? My horizontal tangent is not the same I'm going to zoom in again. This is fun. It's not the same as, look at this. Is that locally linear? No. If it were locally linear, as I continue to zoom in, it would stretch out and appear more and more like a line, like the smooth train tracks that we were talking about. Gosh darn it. This is fun. I like math. So we need to probably put a statement here. So what have we found? F is not plus here, differentiable at x x equals 0 and a reason? Because the left-hand slope, that is the limit as x approaches 0 from the left of f prime of x, does not equal the right-hand slope. That is the limit of f prime of x as x approaches 0 from the right-hand side. How you guys feeling? Great, me too. Gosh darn it, I'm feeling great too. All right, so what other things can be thrown your way? Well, oftentimes you'll be asked to determine values of different parameters that ensure either continuity and or differentiability. So let's lump it all into one. Since we know that a requirement of differentiability is continuity, let's go ahead and find the value of a and b such that the following function is differentiable at x equals 1. That will force us to determine continuity. If we don't have continuity, then automatically we're not differentiable. So first, let's go ahead and determine continuity. Riley gave us an equation for our function to be continuous. As x approaches my break-even point, in this case, x equals 1, what do we need to be true for continuity at x equals 1? Right, what do we need? Vivian? Absolutely. So we need f of 1, the value of my function at x equals 1, to equal the value of the overall limit. So for my overall limit, I need left-hand side to match right-hand side. And for function value, I need a straight eval at x equals 1. So we want to do the function eval first. You told me f of 1 exists if my first equation produces an output when x equals 1, because that's or equal to. Yes? So what do? Well, we simply plug in 1 to my first equation, my top definition, and what do we get? A times 1 squared, we're getting a, plus b, a plus b plus 6. Is that what you guys are getting? That's f of 1?
Yep.
Great. We need that to equal the value of the overall limit. And what do we need for overall limit? We need a left-hand limit. That is the limit as x approaches 1 from the left-hand side of f of x. Which function definition do I use for that? Well, top again, I get the same thing. When I get a plus b plus 6. Left hand limit. Now we need right hand limit. Right hand limit, I'm going to use a different function definition. As x approaches 0 from the right hand side, I'm going to use the bottom definition, 2a minus 3bx. As x approaches 1, what does that expression go to? Right, as x approaches 1. Kobe?
2a minus 3b.
2a minus 3b. If my function is going to be continuous, which is a requirement for differentiability, what must be true? What has to be true here? Danny?
Two limits have to be equal.
Absolutely. I need the left-hand limit then to match the right-hand limit to equal a plus b plus 6. So what are we going to do? Well, we've got one equation now. I need a plus b plus 6 to equal 2a minus 3b. That's great, and that's important. In fact, if this equation is not met, then there's no hope for it being differentiable. However, I have a single equation and how many variables? Two variables, in this case parameters, but two unknown parameters. And so, do I have enough information to solve? No. What haven't we tapped into here? Or what else do we need? Our derivative, right? We need differentiability. In order for differentiability, right, to exist at x equals 1, what has to be true? Right, just in words. What has to be true for my function to be differentiable at x equals 1? Marissa and Brendan?
Like the slope of the left-hand limit and the slope of the right-hand limit have to be equal.
Absolutely. So we've generated one equation here based on continuity. Now let's consider our left and right-hand slope. So now we'll consider the limit as x approaches 1 from the left of f prime of x, and that equals the limit as x approaches 1 from the left of which definition? We'll use top. The derivative of my top, then f prime of x, is power rule. I'm getting 2a x to the first plus b plus 0. Is that what you guys are getting? So for my right-hand slope, as x approaches 1, I'm getting 2a plus b. Remember, the limit of a constant is the constant. So you still have this b here. You guys see that? So what do you guys get? 2a plus b. Now we need our right-hand slope. That is the limit as x approaches 1 from the right of f prime of x equals, go gadget arm. The limit as x approaches 1 from the right of bottom definition. The derivative of 2a minus 3bx is what are you guys getting? It's negative 3b. 2a is a constant in x's eyes. When I differentiate with respect to x, the derivative of a constant is 0 minus 3, right? B is my constant multiplier, so negative 3b. As x approaches 1, what does negative 3b approach? The limit of a constant is the constant. So I'm going to get negative 3b. In order for my function to be differentiable at x equals 1, I need the left-hand slope, shown in red, to equal the right-hand slope, shown in black. Therefore, I have 2a plus b equals negative 3b. I have a new equation. So I can now go ahead and two equations, both in blue, two unknowns. I now have enough information. So what will we do? I'll go ahead and solve this first one. And I get, you want to do A or B? You don't care?
Okay.
A equals negative 4b divided by 2 is negative 2b. Is that what you guys got? Negative 2b? I'll put an asterisk next to this. Great dog, watch where that lands. And substitute it back into my other equation, everywhere I see an A. Sorry, I want a little more space. So I'm going to rewrite this. A is now negative 2b. So negative 2b plus b is negative b plus 6 equals negative 4b minus 3b. Everybody check, make sure you're checking me. 6 equals negative 6b. B equals negative 1. OMG, KT, Sydney, BFF. Oh, I'm feeling really good about this. If b equals negative 1 and I have a place, right, you know, this fat asterisk right here, what a equals negative 2 times negative 1. So a must equals 2. So it looks like we need a to equal 2 and b to equal negative 1. All right, what am I dying to do now? I'm dying to check it. So let's go ahead and do one more emulator workup. We'll be good to go. I'm going to y equals clear. I'm going to zoom 6. And I'm going to enter my leftmost function. But I'm going to do it on my home screen. Guys, on my home screen, I'm going to enter my a value 2. Enter. I'm going to store it in alpha A just so I can enter those exactly and not mess up. So what I'm going to do is I'm going to store 2, my value for A, in alpha A. I'm also going to put my B value, what do I get for B? Negative 1. I'm going to enter it and then store it in alpha B. Why? Because it was B. Now when I go to my y equals menu, I'm simply going to enter my original and not worry about messing up. So I'm going to enter ax squared plus bx alpha b. Did I get it? I did it. It's all right. Everybody's happy. Put on your happy face. And 2a alpha a minus 3bx alpha b x. Got it? And I want to see what's happening right around x equals 1. So my window should include x equals 1. And I'm going to go negative 3 to 3. And I'm going to go negative 5 to 20, because I've already looked at this. And just one PDF. Well, sorry. Moment of truth. X approaches 1 from the left. Uh-oh. How can I tell? I didn't do anything. Because I didn't do the piecewise. That's no good. That doesn't help us at all. What do we need? We need a domain restriction. How do I do that? Easy cheesy. Divide by quantity. Domain restriction. I want x is less than or equal to 1. So x is less than or equal to. Second math test 6. 1. Did I get it? Yes. And I want greater than 1. Love the feet. Come on, fast fingers. Okay. This is what I really want. And that's what I really want. And here we go. Moment of truth. Can we get on our calculus PC train? And we're riding together. And we're still riding. And then, oh no, there's a. Do you guys see? We almost went off the ramp and had one of those wrecks. It would be the 3rd time this week. Do you see that 3rd time this week? But no. It looks like we're caught. Okay, so what do we want to do? I'm going to trace. Well, first I want that. Badly. Then I want to trace 1. And it's going to give me 7, right? And now I'm going to zoom to enter. And there's our ramp. Oh, but we're okay. Look at that. You see that? And if I do it again, right? If I do it again right here.
Oh my God.
And, right? Here's my ramp. And could be bad news, but then, so if we continue zooming in, right? If we continue zooming in, we're going to stretch out our train track and ensure that we're smooth and well-behaved differentiable, and that's locally linear. And so we kind of glossed over that in AB, but this idea of locally linear or local linearity is very important for our differentiability. So that's pretty awesome. Good, great. That's pretty cool. Okay, so what questions do you guys have about our algebraic determination of continuity versus differentiability? Yay, okay. So for our closure then, for f to be continuous at x equals c, what equation must be true? No giveaway, guy. For f of x to be differentiable at x equals c, what equations must be true? I think that's all we need, right? That's a good closure. That's everything? Yes?
No.
Some true false, baby. All right, with infinite corners. All right. So is that enough time?
Yes.
Okay, so for f to be continuous at x equals c, what equation with f's and x's and c's, right, must be true? Tyler?
The limit of f of x as x approaches c equals f of c.
Awesome, thank you. Raise your hand if you have the same equation for number 1. Number 2, what equations? What equations must be true then for number 2 to be true, right? If we're differentiable, then what equations? Was that a typo from Mr. Fritz? No, because he's drawn more attention to it than he would normally draw to his own mistake. What equations must be true? Courtney? Yeah. Yes. I am slow. I get it. No, I get it. I'm slow. Okay, thanks. So we need that one to be true. And what else?
And the limit of f prime of x as x approaches c from left is equal to the limit of f prime of x as x approaches c.
I know we've done a good job. You guys are nailing our differentiability equations, 2 that we needed, so that's pretty awesome. Way to go. And you're wondering why it's not there?
Yeah.
And the answer is I don't know, but now it's back where it belongs. Thank you, Courtney. That's absolutely right. Raise your hand if you have the same thing as Courtney. Equations. Good job. And true or false in the corner. Here we go. For a function to be continuous at x equals c, f of x must be differentiable at x equals c. True or false, Sydney?
False.
Raise your hand if you agree with Sydney. Keep your hand up if you're willing to share number 4. Out on a limb, taking a risk in front of your classmates. Fear of being judged, okay? And Marissa?
True.
True, yes. For a function to be differentiable, it has to be continuous, right? Because we need to be able to hang that tangent line somewhere and be local linear without the gap in our train tracks from our story if we continue zooming in. Yes? You guys are awesome, and that's a printable, and I couldn't quite do all odds because there are just some evens that you had to do that were just that good. So while I tried to make most of these odds, if you'll notice, I want you to draw your attention to number 39, 40, 41, and 42. There's 2 evens. Okay, there's 2 evens on there. The rest of the time it's going to be yours to work. Yes, and you got a solid 15-minute chunk. I'm going to pause and save the recording. Way to go, you guys.